What we're going to do now is basically something called saponification. This is taking an ester in base and converting it to a carboxylate. So you would need to have first off an ester. I'm going to keep it as a very simple ester. And what you're going to add to it is hydroxide in water. So that could be in a variety of different forms. I'm going to use sodium hydroxide in water. The point is you have a hydroxide, and it is going to add as a nucleophile toward the carbonyl carbon as long as there aren't any more acidic protons present, but I don't think there will be. So add it to the carbonyl carbon. Can't have 5 bonds to break the pi bond so that you can make the tetrahedral intermediate. And this is a negatively charged tetrahedral intermediate. And this is done in water. Now there are actually 2 things you can do here. I'm not going to do the one, but I'll talk about it. This negatively charged tetrahedral intermediate may pick up a proton from water to make a neutral tetrahedral intermediate and a hydroxide. That is fine to do. But the point is, if you do that, you have to rip the proton off in the next step. It's kind of counterproductive. It may happen, but you're going to have to lose the proton as soon as you put it on, so I'm not even going to bother to put it on. What this oxygen is going to do, though, that has the negative charge, is reform the pi bond to the carbonyl carbon. That means something has got to go. Now, as you look at your potential leaving groups of a CH3, an OH, or an OCH3, you need to consider which one will be the best leaving group. That is not going to be the CH3 group. That would create a much stronger base than what you started with, so that's out of the question. The OCH3 minus and OH minus are about the same basicity. They're pretty much exactly the same. So either of these 2 groups could kick out. And it really doesn't matter which one it is. But we're going to kick out the OCH3 group because that's going to give us productive chemistry. And that's really the only reason why I'm choosing that one over the OH group. But you are going to reform the pi bond and kick out a leaving group. And again, I am really not making a stronger base, so that's why this is acceptable. And this really is an equilibrium reaction. So once that has occurred, you make the carboxylic acid. And you have your base. Now methoxide is still a pretty strong base. And carboxylic acids are weak acids, so it's actually going to come in here and remove the proton and give electrons back. And this is really the driving force for the reaction, because by doing so you're going to make a weaker acid-base pair. You're still going to have a base in the carboxylate right here, and then you'll also make the corresponding alcohol. And this carboxylate does have resonance delocalization of its negative charge. So it's fairly stable. And this is where you will stay until, in a second step, you add some form of acid. So you do need to pick up a proton eventually so you can isolate this carboxylic acid. But you don't just do this. So you add an acid, pick up your proton, and then eventually you will have a carboxylic acid. But again, that only happens after you add acid to the solution to neutralize it.